So now present the Hypersolver project. And first, the principle of the concept. Jean, could you come? I think we have to be here, to be seen on the. This is the correct position.
Thank you, Jean-Louis. So, good morning. I'm pleased to present Hypersolver. So first, the concept description, then we'll describe briefly the AI design and architecture. Then Jean-Louis will present the technical platform, the one we use to train the AI models, but also to support the validation exercise. Then Matteo will present the AI performance results, and Yutong from Singapore remotely will present briefly the ATFM part of the project, and Victor from LFV Sweden will present the results focusing on the ATC part and the ops feedback. So this project is a collaborative effort between some partners, Neometis, ENAC, Eurocontrol, LFV, the Swedish NSP, the NTU, Singapore, and the University. Well, sorry? And the University of Warwick in UK. This project at first is to explore if AI, and in particular AI digital assistant or human AI teaming, but if AI in particular deep reinforcement learning can provide a solution for the future. So for decades now, for me for 35 years, we try to develop numerous solver for the ATFM part, but we created the CASA algorithm for ATFM 35 years ago, and this morning we are still using this one. No one replaces something in the ATFM part. I work also a lot in the ATC part to try to develop, in particular, conflict resolution, and I think we are numerous. A lot of people here working on this area. I'm not sure this morning there are some ops in Europe that really work with a automatic conflict resolution tool. Okay, so it's the reason why we propose this project in order really to explore if new AI opportunities, in particular, deep reinforcement learning can be a magical solution for us. And to look together, to look if we can integrate ATFM and ITC in a single framework powered by AI. It means, can we develop a unified AI solver, both to solve DCB problem and the ATC problem? Because today we are working in isolation. Never nobody try, okay, if I'm developing a conflict resolution, maybe I can also use this approach for my ATFM part. Deep reinforcement learning is interesting because we can manage what we call long-term reward that Matteo will explain a little bit. It means that we can maybe try to optimize both ATFM and ATC. At the end of my presentation, if I have $1 million, I will indicate if I will invest or not my $1 million in such an approach. And it's aligned with the CESAR vision in order to try to develop digital transformation, and in particular, AI digital assistant and human AI teaming. So today, ATFM and ITC, they are managed separately. Even from at least the last 20 years, we try to fill the gap between ATFM and ITC. If today I look, ATFM is still mainly in the planning phase, and ITC at the sector level for tactical intervention. If I look the time frame, 1 hour time horizon, 40 minutes time horizon, we can say there is nothing. There is nothing. There is no real strong ATFM measures for airborne flights in this time frame, and there is no ATC activity in order to anticipate potential conflict or to prevent conflict or to dissolve conflict in a 40 minutes, 30 minutes time in advance. Maybe here there is a room of opportunity in order to consider ATFM and ITC, and in particular to merge this one in order to have something unified. So today we have conflicting strategies because ATFM or DCB or DFMP, it detects a problem. You want to solve the problem. On the ATC part, it can detect the conflict. You want to solve the conflict. And okay, we try to have something integrated, but at the end, probably we have conflicting strategies and loss of capacity. Also, the airspace is saturated, sectors smaller and smaller, and the traffic is growing now, recovering from the COVID period. So, with this sector-based approach, we have strong limitations. So now the question, if we have so powerful EI tool to detect a problem and to solve conflict, I remember that for you, the actual two position with two controllers was it was invented more or less 1 century ago in US, and we are probably, I don't know if it's for the eternity, but we have one sector with limited size with two controllers everywhere in the world, and for now a century. So with such powerful tool and EI digital assistant, do we want to keep this approach or can we explore something else? So here in our project, we try not to look at the sector level, but if you want, at the cluster of sectors, a size that can represent 3-4 sectors in order to have something, in order to have a more anticipated horizons, okay? But in such sectors, we cannot work like today. So it's the reason why we shift from what we call sector-based to flight-centric. It means that a controller will be responsible for, we manage a set of flights from end to end in this large sector. It means also we can have maybe 3, 4, 5 controllers in such a volume. In the demo that we will present this afternoon, 3 controllers operated during the validation exercise in the same volume. Also, control by exception, it means that we need to design a system closed loop. We need to have a 4D trajectory closed loop in order to be able to reduce the uncertainty, to improve the prediction and to allow the EI to run correctly. And today we are working in an open loop system. Also, what we are looking for years now is to take opportunity or benefits of new FMS capability, in particular the EPP. And in fact, the question, if we are looking in the time horizon 40 minutes, 60 minutes, with such EPP capability, can we have enough precision to predict what will be the position of the trajectory in 30 minutes? It will help us a lot to design a system that would be able to detect a bunch of flights or conflicting flights in advance. So we adjust a little bit the ATM layers. Today, more or less, you have the ATFM in the planning phase to deal with the regulation, the ground delay, and the conflict at the sector level. What we have introduced in the 60 minutes, 20 minutes time horizon is a layer named proximity in order to detect potential conflict in advance. And also the bunching is the ATFM part for airborne flights. Because maybe we don't know. We apply regulation today on the planning phase, maybe a large part of this regulation should be managed for airborne flight, maybe 1 or 2 hours in advance when the flights are airborne. We don't know, in fact. So it's what we started to try to explore in this project. So I think really it was world first to try to apply deep reinforcement learning, these models really to real traffic. So there are a lot of issues, the complexity of situation and the scalability, but we try to address at least the conflict and the proximity part. Also, it was not planned like that at the beginning of the project, but what we have identified during this 2 years project is to consider a new role for the supervisor, and his role can be really to monitor the controller's activity. It means the workload, the safety feeding, and other metrics, because he is working with his EI colleague, and also to monitor the EI performance. And his new supervisor role to monitor and to be able to take decision in order at any moment to adjust the goals and the EI autonomy, and also to be sure that the situation provided to the set of controllers is comfortable. So if we summarize, we have 3 humans: the pilot, the controllers, the supervisor. So the AI is able, in such a perfect world, to detect any problems and to solve and to provide solutions. So he will provide the solution. He will inform for any solution. He will inform the controller. The controller has to acknowledge, but he can also adjust the EI proposal. It's kind of hybrid human EI or human EI teaming. And the EI, after validation, control validation, can directly send the CPDLC clearance to the pilot. Okay. For some situation when the conflict is a very short term, we can say 3, 4, 5 minutes before the conflict will happen. Due to CPDLC latency time and issues, we need to use the VHF clearance, and it's mandatory that for all these specific situations, the controller will manage itself the clearance. The supervisor is monitoring the human performance and the EI interaction, and will be the master to adjust this human EI teaming. We started to develop what was called in the human EI teaming community the playbook. Playbook is a set of predefined scenarios, goals, objectives, in order to, okay, if I have a controller with high workload, or if my EI performance is not so good, in order to apply predefined scenarios to adjust to, for example, to reallocate flights from controllers to other controllers, or to stop some EI agent components in order to adjust the human workload. That's all. I propose to keep all your questions at the end of the presentation. And now Matteo will present his EI design and principles.
Yeah. Thank you, Gilles. Sorry for my voice. Is the period, unfortunately, is not. I still have a bit of flu. So I am the data scientist that work at the development of the AI solution. And as Gilles said, I'm going to show you the main AI principles behind Hypersolver. So basically, there are two. That is reinforcement learning and graph neural networks. Reinforcement learning is a quite peculiar type of artificial intelligence because usually, not always, but usually, we have a target and we want to predict this target. But in the case of reinforcement learning, The setting is what you see in the image. So basically we have an agent and we have an environment. And the agent can take actions in the environment and also has a task that is a mission that it has to accomplish. And the general loop of interactions between the agent and the environment is that the agent observes the current state of the environment, and according to this, it decides an action to take. It takes the action, and once the action is taken, it receives the new state of the environment, so how the environment was changed by its action, and a reward. A reward, we define it, is simply a numerical signal that is related to the objective. And so it will be higher if the action taken is beneficial to the mission, and it will be obviously low if the action taken is detrimental. And this loop of interaction, just for your information, is divided in episodes. So we have usually a starting state that can be always been the same, or it can vary according to the problem. And then this interaction of observation, taking action, reward, and so on arrives up to an ending state that, for example, in the case of Hypersolver, could be when there are no more flights to control. And the last component of this setting is the policy, and the policy is simply the strategy that the agent uses to choose the actions that he takes. And the goal of every reinforcement learning algorithm is to find the policy that maximizes the reward over time in the episodes. And since this is correlated to the objective, in theory, this is the policies that will solve at best the task. And this is done running a lot of episodes with a simulator both of the environment and the agent. So you run a lot of episodes, you try a lot of solutions in various settings, and hopefully you find the best policy. Obviously, in the case of Hypersolver, the agent is the outcome system, the environment is the control sector, and the objective are the ones that Gila said about avoiding conflicts and also general route optimization. The second concept is graph neural networks, and we have to use graph neural networks because we define the control sector as a graph. So each flight is a node, so it has its own characteristics like the destination, the altitude, the speed, and so on. And it is connected to every other flight, so it's features are proximity measures between the two flights. So in this graphing condenses all the flights and also the and obviously graph networks are easy to handle graphs, and so it was what we had to use. And the advantage of this setting is that we can produce an action per node, so an action per flight, and this means that we can handle, since the graph neural networks can handle graphs of various length, we can handle a varying number of nodes, so the number of flights in the sector will change, obviously. And this is fundamental in our problem. The policy is also spatially agnostic because we use relative distances between flights. So we don't rely really on the geography of the sector for the algorithm. So theoretically, a model that is trained on a sector can be used also on other sectors. And the action that we chose was the next waypoint for the flight before pointing back to destination. So the idea was that combining reinforcement learning graph neural network was possible to train a flexible policy that was able to handle a varying number of flights and also scenarios. And now I think is Jean-Louis that has to present the technical part.
Thank you very much, Matteo. I will present you the technical platform we have developed to, for this project. So what is the problem? We have to create a simulation with different inputs. So first, the geometry of the airspace, the air traffic unit, and taking into account the physics of the aircraft for all the different types of aircraft, and then reuse real traffic for the validation to create scenarios that we can adjust to create some conflicts to be solved. But most of all, we have to train an AI system So we have to create a kind of interface with this software to allow modification coming from it to solve the conflicts and to present the actual situation of the airspace with the location of all aircraft, etc. So for that, it has to be standard. We used a standard library for that gymnasium. And also for the validation, we have to create some positions to test how would react the human, seeing the proposals of solution, conflict resolution coming from the AI. So what should we choose for such a simulator? At the very beginning, it was completely open, but we knew that there was no existing simulator that was able to deal with both ATFM and ATC problem. So we had in mind three solutions. First, to use a simulator developed by Microsoft, AirSim. Second one was to use a simulator developed by TU Delft, Blue Sky. And obviously, the last solution was to develop a new simulator. So Microsoft was part of our consortium at the beginning of the project and left at the beginning of the project. And then it became difficult to use AirSim. In parallel, we started a survey of the other options, and it appeared that the Blue Sky was difficult to master. And we were somehow dissuaded to use it. At that time, I didn't know that TU Delft had a program to develop AI in Blue Sky. And in order to assess some AI software. And I learned it in Rome for the last Cesar Innovation Days, when I met Jan Roth, who was in charge of this thing. If we knew it at that time, we probably considered cooperation with this development. But at the end, we decided to develop from scratch. And it was a bit crazy because we had less than 1 year. And of course, we ensured Cesar GU that we would do it for the same price. And so the advantage was still to master completely the simulator, not to spend time to learn how to use it. And we were told that minimum was 3 months with Blue Sky, for example. And it was an opportunity to create a small piece of software dedicated for our project that was supposed to be fast and efficient. Of course, in every project, you encounter a lot of problems. And here I listed some of them. I would say this is the normal life of a project. There is many things you did underestimate at the beginning. So, for example, extracting routes from SO6 file from DDR Eurocontrol file is not a piece of cake. First, it's difficult to get the file. You have to negotiate with Eurocontrol. And then when you have it, find your data within it is not that easy, especially for the ATS unit geometry, which is rather complex. It's the description of three-dimensional volumes interconnected, and it's not easy. So not expected, but we did master that. Then we had a lot of problems with the geometry. A lot of calculation, or depending on this question, is the waypoint I'm considering in the action? It looks a very basic question. A human being sees image, yes, it's inside if you see the picture. But from a software point of view, it's a big problem. It's a source of complexity because you cannot imagine at the beginning that you have a lot of subcases that are linked with the convexity of the shape. And for example, you will give an order to divert a flight 10 degrees left on 40 nautical miles. Fine. The resulting point, where is it? Is it inside or outside your ATS unit? Difficult to define. And because of the closed loop principle, you need to know because the action could be allowed or forbidden. So it was a big issue, in fact. And then the definition of the HMI for to conduct the validation, I think we had a lot of discussion with the users, and I want to thank them because it was just impossible to create a real ATC system, and we found a way to create the minimum functionalities that were realistic enough to assess the concept. And of course, it's very simple at the same time. It's not a proper system. And then we had the validation scenarios. I was not expecting that we would have to develop some tools to adjust the scenarios, but it was not that difficult. And then we totally underestimated the integration. It was 0 days on our project, and it took some time, I would say, because all our software was developed in Python, and we had to integrate a piece of software developed in Java, for example. And we experienced some problem for LFV to use the system remotely. We had this great idea that, oh yes, we are going to use a complete decentralized solution with server, and it would be possible just to connect via internet. Yes, but the connection was blocked by the LFV system, and they were not able to assess the prototype remotely for a long time. Of course, the tuning of the platform took a lot of time. It was too slow to configure the server, etc. And also the post-operation analysis, again, the geometry introduced some problem. But those are normal things that happen in a project. The real problem was the performance. It was too slow. And the target was to be able to perform a training within a day, maximum 2 days, and it was not the case. That's what I'm going to develop now. So everything was fine until we got this slide in a presentation of a progress meeting with our partner, the University of Warwick. So it shows that we cannot train more than 2 flights, with more than 2 flights, where we were expecting about 250 flights at the same time. And their estimation with the simulation they had at that time was that it would take more than 1 year to make one training with 250 flights to able to deal with 250 flights. We had less than 1 year to complete the project, so it was not possible. We knew, of course, that we would have to optimize the software. We had planned a couple of weeks for that. So that's what we did at the beginning. The first step, we tried to optimize the software. We cached some geometrical operation to save time, of course. Optimize the geometry and geometry operations, simplify the piece of software that was spending too much time. Try to locate where was the problem, optimize the software, parallelize actions, especially the integration, and vectorize some operations as well. We did not vectorize everything. That's why it's written in gray, because to do that, we would have to destroy completely the structure of the software and make it completely unreadable and unmaintainable. So we didn't do that completely. But once you have done that, and still it's too slow, you have to simplify the problem. And then we try to find solution. So the first idea was to simplify the shapes of the ATS units. So here you see an example. This is not the final shapes on the right side that we used. There is some problem. There is, but this is the idea. You see how we did cut the shapes. We didn't do it completely because, again, it would help a lot if every ATS unit was completely convex. And it's not the case here, because if so, we could remove a whole part of the geometrical calculations. So we did what we could. It was a kind of balance between the to have a realistic simulation and fast enough simulation. So another idea was, because there was no good result, we can skip some actions that were foreseen. That is the change in altitude and speed. So after that, all the flights were on a plan, and it did simplify the problem for the AI to be trained. We removed all the restricted areas. Of course, it was developed for nothing. And we reduced the number of flights because it was a critical part. But we said we cannot be under 80 flights. So it was the target to create a model that can handle 80 flights. And by doing this, we reduced the processing time by more than 70%. And it was not enough. It was a great optimization. And then we started to see how we could ease the training and try to find ways to accelerate the training with this simulator. So first, we removed all the kinematic parts of the aircraft models, thinking that it was an approximation. But if we can create a model with that, after that, we could make another training more accurate with the kinematics. That would take more time, but we have to be close to the solution first. And there was some technical solution also to speed up the training, and try another algorithm maybe for the AI that would converge faster and this kind of thing. Okay, the most idea was to start simple and to make it more complex. There's one thing we didn't consider. It was to change the platform. There was no time for that. At the end, we are happy. There is we have a system that is able to simulate with a good accuracy and reproduce the aircraft evolutions, and it is designed to be interfaced with an API system, and it emulates both ATC and the ATFM layers, and so it's rather small. It's a good system, I think. So that's all I wanted to say about the development of this platform. Now I will leave Matteo tell us about the results.
We'll go quite fast because I think we don't have a lot of time. Yes. Okay. Regarding the results of the algorithm trained on the solution that we just explained, obviously, as not every, but most of machine AI solution, it must be trained. So this is the setting that we used for the training. So we trained on the exercise scenario, and we trained with 50 flights. So the starting state was always with 50 flights at the start of the episode, and we set the conflict threshold to 10 nautical miles to make the problem more complex during the training, because we were particularly interested in avoid conflicts. And since the APCOs could modify the actions of the algorithm during the exercise in general utilization, we also changed the decisions of the model with 2% probability randomly on every flight. So this should have also mimic this kind of problematic. And regarding the results of the training by itself, they are synthesized by these two graphs on the right. And the first one is the reward over time during the episodes. And you can see on average it goes up and arrives to a plateau. And in general, when you arrive to a plateau, it's worth it to stop the training because it's not going probably to improve any further. And the second graph is the entropy. And entropy is just an uncertainty measure. It just tells us how much the model is confident of its decisions. So by itself is not very informative, but a low entropy. So a low entropy means a great confidence. On pair with good results on the reward is a really good sign. And regarding some metrics that are more of interest for you, I think, that are related to the ATM problem. We have the episode length over time, so this is the number of interactions between the agent and the environment. And you see over time, they decrease from 130 to 90, so it was able to handle the traffic more efficiently. And on the right, you have the real goal that we wanted to achieve, that is the number of conflicts in the episodes. And you can see that by the end of the training is approached on average to 0. That is what we wanted. And finally, just a few words on the performance in real traffic. So what we noticed is that for low and medium traffic, the performance were already quite good. And in general, there was good resolution of conflicts, and the solution was also, I think, quite understandable. Instead, for high traffic, the model still has some performance issues. And also there is low AI transparency, so it's difficult to understand sometimes what it's really doing. So the two key recommendations from the exercise were to improve the performance obviously in high traffic and give more in general, but especially in more complex situations, give some tools to have some kind of explainability of what the model is doing. And that's it. And now it's Yuzong. I don't know. You yes.
Yeah, thank you, Matteo.
Yeah, I can.
I think you will have to.
Yes, I can. Yes,
thank you.
You can tell me when you need the new slide. Okay, you don't.
Yeah,
You hear me?
yeah, I'm ready. Can you hear me?
Okay.
Yeah.
Yeah, okay, please, next slide. Thank you. Yeah, okay, I have to introduce our developer DCB to you. So our work relies on two main sources. First, historical European flight plans in SO6 format from December 16th to 22nd, 2019. Second, 9 ATS unit boundaries generated by our partner Neomasis based on realistic European sector layouts. From these, we computed the planned entry times of each flight into each ATS unit, transforming this into flight demand data. Given that the real capacity of this artificially constructed ATS unit wasn't available, we estimate ATS unit capacities by assuming a maximum overload of about 10% in the historical flight plans. These estimated capacities, together with the demand data, were fed into our DCB solver. The solver identifies which flights require regulation and computes their ground delays. We then integrate these delays into the original SO6 fields to generate regulated flight plans, which serve as traffic input to the project simulator. Next, please. Hello, next slide, please.
Again?
Oh, yeah. Thank you. For no, previous.
Okay,
Last.
it was
Last. Yeah. Thank you.
very quick.
Yeah. For
Okay.
yeah. This one. Yeah. Hotspot emulation. Yeah. Following the Hypersolver operational concept, the day is divided into 12 regulated blocks, each spanning 2 hours. For each block, the DCB solver is performed 1 hour in advance. The top left animation shows the 12 blocks being processed sequentially, while the color grid shows the demand to capacity ratio. Red indicating overload, that is hotspots. The top right of the animation tracks the cumulative number of regulated flights and the total delay time. We can observe that hotspots in each block are eliminated and the regulation numbers grow accordingly. The bottom left chart, focusing on ATS unit ES as an example, shows that after DCB, all time windows demands have been adjusted below capacity, achieving a clear peak shaving effect. The top right chart summarizes the number of hotspots per data site. In summary, our solver eliminates all hotspots. In fact, theoretically, as long as unlimited ground delay or cancellations are allowed, hotspots can always be eliminated. Next slide, please. Yeah, okay. Here we present 4 key delay indicators across the project data sites. That is average delay for delayed flights, average delay across all flights, maximum delay, flight delay rate. The red dashed line marks the average across the 7 data sites. 2 of these metrics can be benchmarked against Eurocontrol historical performance reports. The historical monthly average for every delay per flight is about 1.18 minutes, roughly 4 times higher than our method results. The historical annual flight delay rate is about 9.9%, whereas ours is about half that. That said, these comparisons are only for reference. They aren't strictly fair, as we assumed capped overload rate of 10%, and we lack historical overload data. Moreover, the statistical methods may differ. Still, overall, the solver delivers practically acceptable delay performance. Next slide, please. Okay, the left side chart show computation time and the traffic volume per regulated block, respectively. We see that solving never exceeds 2.9 seconds per block. The computation time scales mainly with the number of total and regulated flights because our solver replans flights one by one. The more flights requiring adjustment, the longer the solving time. Higher density, more complex scenarios also demand more computation. In summary, the computational performance meets Hypersolver's operational requirements because it can be solved in an hour. Okay, that's all from my side. Thank you. Okay, let's move to Victor.
Okay, thank you. So my name is Victor. I work at Swedish Navigation Services as a validation engineer, and I will give you a short presentation about the feedback from the atlas during the exercise. As you already heard, Hypersolver, we assess the Hypersolver concept and the AI supporting tool across both ATFM and HC phases. And the plan was also to evaluate the teaming aspect with the playbook in a synchronous operation and flight-centric context. So the exercise itself was a real-time simulation involving professional ATCOs. It was 2 ATCOs from LFE and 1 from Eurocontrol. And we had 3 working control working positions during validation and 1 supervisor position. And we explored various operational configurations with and without the Hypersolver assistance. And the airspace that we used was part of Germany, Belgium, Netherlands, Denmark, Sweden, and France. It was only en route environment, and it was from flight 250 and upwards. And as we already know, that it was limited to lateral conflict resolution only. And you have already got a lot of information about the technical environment from John. So we move to the next slide. So as I said, the exercise was performed in flight-centric HC setup with single controller operation environment with the teaming human AI teaming aspects. We used 3 traffic densities, low, medium, high, and 3 operational configurations together with the traffic densities. So we performed 9 runs. So 3 configurations for each traffic, and then some additional runs as well. So you can see at the bottom here, the first configuration was the operational manual mode, which was when the controllers worked manually with the traffic without the AI. So this was like a reference. And then we did the configuration when controllers followed the AI solutions. And then the last one was the hybrid configuration. And the hybrid, they could interact with the AI, obviously. So they could accept or decline the solutions. Here we can see a diagram of the workload. It's also the Bedford scale from 1 to 10. And for the first like low and medium scenarios, the workload was very low. And it was also unbalanced. Then we can see that the higher traffic scenarios, the workload increase a lot, and also a little bit unbalanced, or a lot of unbalance we can see between some of the controllers. Situation awareness for all the controllers individually. As you can see, the first low and medium traffic, the situation awareness is between 3 and 5, so okay to very good. And it also reflects the unbalance in how many flight or conflicts each controller were assigned. And then during high traffic, less situation awareness. So some conclusions. The concept and AI, together with AI, showed some potential in mainly simpler traffic conditions. And the feedback indicated that also from the controllers that the proposals were mainly considered safe. And the AI solutions also always included closed loop clearances. However, in several scenarios with high traffic, the AI gave very few suggestions sometimes, or stopped acting, which forced the ATCOs to revert to manual conflict resolution. And some of the AI proposals were observed as maybe not the most optimal, sometimes very large deviations near the boundaries or repeated suggestions. Yeah, so both the single control operation and the flight centric was rated as neutral to positive in terms of acceptability from the controllers, but obviously not suitable for high traffic densities and complexities at the moment. But they expressed the interest in trying the concept in sector-based operation as well. And the human AI team showed positive signs, but sometimes the system provided limited support, and situation awareness, as we saw, could be improved with more using maybe more advanced HMI, and that the controllers had more of the tools that they are used to in the system. The feedback also include positive experience when allowed to work in hybrid, especially to engage with the human and AI teaming aspect. So I think that was all from my side about the results. So thank you very much.